I want to turn this over to our presenter for today, Mr. Dan Gill. And he's Gill, he's the water treatment superintendent at East Bay Mud. Welcome, Dan.
Thank you, Robert. And good morning, everyone. I'm the water treatment superintendent for East Bay Mud, and the focus of this presentation is T3, T4 exam prep. If you have any questions, I think there's a chat box, and feel free to chat away. So first of all, when you take your state exam, one of the first things I'd like to do is look over on the California DDW website. There's a drinking water treatment exam expected range of knowledge. And if you're focusing on the T3, T4 exam, you can kind of see the breakdown of the questions. T3 being heavy in the water treatment process, and the T4 being a little bit heavier on the regulations, administrative duty portion of the test. And that's broken down a little bit further on the bottom. Getting right into it. Sources of water. Okay, where do we get our water from? Okay, desalination, obviously that's water treated from the ocean. Surface water, which is the bulk of where we get our water from, reservoirs, streams, dams, lakes, and groundwater, which is water that percolates after rain to an underground aquifer, which can then be pumped to your water treatment plant or directly to a system. Water rights. Many potential drinking water sources are unavailable because the right to their use are already allocated. Depending on state laws, water rights may be sold, leased, or transferred like other property. So every utility is going to have right to a certain source of water. And some water utilities or irrigation districts actually sell water to many different users. Sanitary surveys, or even if the water rights are available, the source of water may not be appropriate for drinking water uses because of the water quality. The sanitary surveys are used to determine if a new source is appropriate or an existing supply continues to offer a safe and high quality water. Sanitary survey is could be on the test, and really, essentially, it's to evaluate the quality of your source water and if it is appropriate for the type of treatment or treatment process you have to do to treat it. Most waters will be treated by conventional water treatment. Other waters need a little bit more, or maybe some even less. Physical characteristics of the water. What am I treating? You're treating turbidity, color, temperature, tastes, and odors. Some other characteristics of treating water are the chemical characteristics, the biological factors, and radiological factors. And a part of treating the water is not only do I need to know what's the physical characteristics of the water, but you also need to manage your source water. And in that's removal of trees, brush, treating the reservoir at times with copper sulfate, livestock grazing, managing that, use of pesticides, wildfires, farming, and use of fertilizers. So not only do we have our source of water in a reservoir, and we have to manage that reservoir to maintain high water quality. And in these reservoirs, and this is a thermally stratified reservoir, which you'll see in the summer, you'll have different layers of that reservoir. The epilimnion, which is the top layer, the thermocline, and the hypolimnion, which is the most bottom portion of that reservoir. And usually in reservoirs, the intake structures, you'll have a tower in which you could choose the different gates to select based on the best water quality. And this is a thermally stratified reservoir, and that's typically in the winter. When you get to, the summer. When you get to the winter months, usually you'll see something different after the reservoir overturn. So in the fall, which is right about now when the days are shorter, the temperature on top of the reservoir cools down, and then the upper layer, the temperatures drop, the upper layer cools and sinks. The result is a mixed reservoir with no optimum layers. So you'll have the same temperature and same water quality characteristics throughout the reservoir after it turns over, which happens usually in the fall and right about now, actually. And what happens, usually you'll see fish kills, odor problems with the water, iron manganese issues. This typically occurs now. And what happens in the summertime, the bottom layer will become anaerobic, the oxygen level will deplete. And when that reservoir turns over, that the anaerobic water will get into the different layers of the reservoir and may result in a fish kill. Moving on to the water treatment process. So we've got our reservoirs, we have to manage those reservoirs, and now we have to treat the water. The first step in the treatment process is coagulation. What is coagulation? The clumping together of very fine particles into larger particles called floc, caused by the use of chemicals called coagulants. The chemicals neutralize the electrical charges of the fine particles, allowing them to come closer and form larger clumps. This clumping together makes it easier to separate the solids from the water by settling. As coagulants are introduced, small particles react and form large, heavier floc. The weight is important because you're using gravity to settle the floc in the sedimentation process. Types of coagulants. You're going to have primary and coagulant aids. Typically, the primary coagulants are going to be your aluminum sulfates, ferric sulfate, ferrous sulfate, ferric chloride, polyaluminum chloride, and each is specific to the type of water you're trying to treat. Coagulant aids are usually cationic, anionic, non-ionic polymers. Metallic salts and synthetic organic polymers are commonly used as coagulation chemicals in water treatment because they are effective, relatively low in costs, available, and easy to handle, store, and apply. Primary coagulant selection. Selection can be difficult because there are so many different types of chemicals and no universal evaluation method. Typically, the primary coagulant of a water treatment plant will have has historically been the same. And there isn't too much change to that primary coagulant. Aluminum sulfate is a very popular coagulant that is used on most surface water. But when choosing your coagulant, you need to consider the approval for drinking water use if it is NSF approved. You're going to consider the cost, the availability, and of course your source water characteristics. Coagulation chemistry, particle destabilization. Most colloidal particles are negatively charged. Most coagulant chemicals are positively charged. So essentially, when you have your colloidal particles in the raw water, when it's untreated, they want to repel each other. And typically, the coagulant that you will use is positively charged, and it will those negatively charged and form floc, which then will settle in the sedimentation process. Alkalinity. The alkalinity of a water sample is a measure of the water's capacity to neutralize acid. In natural and treated waters, alkalinity is caused mainly by bicarbonate, carbonate, and hydroxide, which originate from calcium, magnesium, and sodium compounds. pH drops slowly as you add acid until all hydroxide, carbonate, and bicarbonate is consumed by 4.5. Titrating down to pH 4.5 measures total alkalinity. Titrating down to 8.3 measures phenolphthalein alkalinity, which most source waters are already near that endpoint. pH. Why is pH important? The pH of the water determines which hydrolysis species chemical compounds predominate. Lower pH values tend to favor positively charged species, which are desirable for reacting with negatively charged colloids and particulates, forming insoluble flocs and removing impurities from the water. So we talked about the alkalinity of the water, the pH of the water, and the reason why I mentioned those two factors there is because it's very important in determining and how effective your coagulant is. Aluminum sulfate from this picture here only works below a pH in specific pH ranges, typically below a 7.4 range, and it's actually more effective at organic removal, even lower on the pH scale. There, in that chemical reaction with the aluminum sulfate with the water, there is alkalinity that must be consumed. So anytime you're at a water treatment plant and you want to use aluminum sulfate as your primary coagulant, you need to monitor your alkalinity because you need an appropriate level of alkalinity in order to properly treat the water. Ferric sulfate is going to be a little different. The pH range is a lot wider for ferric. So aluminum sulfate has a lower pH range in which it is most effective. Ferric has got a wider range. So depending on your source water characteristics, if you have a pH range that's much higher, you may want to consider ferric, unless you want to do a pH suppression system on the front of the plant. Enhanced coagulation. Enhanced coagulation is a process designed to remove natural matter from water by adjusting both the coagulant dose and pH to produce the greatest possible reduction of dissolved or suspended matter. So normal coagulation, we're looking for turbidity removal. Enhanced coagulation, we are trying to maximize organic removal. Why do we want to enhance organic removal? Because we want to limit disinfection byproduct formation, DBP, most specifically in total trihalomethanes or HA5s, haloacetic acids. Enhanced coagulation is paramount to reducing TOC and thereby reducing DBP formation, THMs. pH reduction depends on the alkalinity of the source water. So in enhanced coagulation, we want to reduce the organic content of the water because chlorine, which is the primary disinfectant in mostly all water treatment plants because of that good, strong chlorine residual, chlorine interacts with organics to form disinfection byproducts, which will negatively affect the system and is regulated. Flocculation, moving from coagulation, is a slow stirring process that causes the gathering together of small coagulated particles into large settleable particles. So flocculation, so after coagulant is introduced, you'll begin to form floc. Flocculation process is used to slow down the water to form a strong floc so that in the sedimentation process, your floc can settle and be removed from the water that then goes to your filters. So I'm not going to focus too much on the flocculation sedimentation process because this class is geared more for the T3, T4 range. Filtration, the purpose of filtration is the removal of particulate impurities and floc from the water being treated. Through filtration, water passes through materials such as a bed of sand, coal, and other granular substances to remove floc and particulate impurities. So filtration to me is one of the most important processes at the water treatment plant. And really your coagulation, flocculation, sedimentation process are to set up the water to be filtered in the best way. There are a number of interrelated removal mechanisms within the filter media itself that are relied upon to achieve high removal efficiencies. These removal mechanisms include the following. Your sedimentation, well, actually this is in reference to a filter. So what is going on in my filter? Sedimentation on the media, you've got particulates that are settling on the media. That's very important. Adsorption through the media. You got to think when you're thinking of adsorption, because filters, your particulates that get past the sedimentation process, they should adsorb in the filter media and continue to block other particulates from getting through the filter. You'll see this recording on your filter as head loss because the top layer of your filter is, it's getting tougher for water to filter through. There's biological action. Adsorption is not too important after initial wetting. And when you think of, absorption, think of a sponge. So that typically happens when you first introduce water to the filter in which the media is, absorbing the water. And straining. So straining is, think of a colander or just sand. When you just have particulates getting strained, whatever you get on the bottom is what's getting through the filter. But really that adsorption is very important to filtration. Different types of filters: gravity filtration, pressure filtration, diatomicous earth filtration, slow sand filtration. Most agencies, most conventional water treatment plants are going to use gravity filtration. Filter media. So you're going to have sand on the bottom of your filter media. You're going to have anthracite coal. Garnet is like a sand that may be used. These are your typical medias used in filters, and they're used because they have good hydraulic characteristics, does not react with substances in the water. It's hard, durable, free of impurities, and insoluble to water. Filter media is usually characterized by the effective size, the size of that media, the uniformity coefficient, how uniform the media is compared to other media in the filter, the specific gravity, how heavy it is, and the hardness. Proper selection of media size is important and based on two factors: the time required for turbidity to break through the filter, the time required for the filter to reach limiting terminal head loss. Properly sized media will result in both factors happening simultaneously with leaning on head loss. You do not want particulates to get through the media. You want the filter to end on head loss, because that means that the impurities, the particulates are not getting through the filter media. Turbidity breakthrough, of course, you want to take out a filter before it reaches your your goal, typically maybe 0.1 NTU at most utilities, 0.3 being the regulatory point in 95% of the samples. But you don't want filters to pass turbidity, because you'll have issues on, when you add chlorine on the other end, it will add chlorine demand. If the limiting head loss is frequently a problem and turbidity breakthrough rarely occurs, then a larger media size may be considered. If turbidity breakthrough is frequently a problem and limiting head loss is rarely encountered, then a smaller media size may be considered. Optimized process, proper chemical addition is also the main contributor of premature turbidity breakthrough or premature head loss. Head loss buildup, typically you'll see overdoses of filter aid and maybe, so you'll see the head loss, but there's always a balance between an efficient filter run. You want to maximize the amount of water you're filtering with, reaching a terminal head loss of whatever your utility feels appropriate and not having the turbidity breakthrough. So there's the balance there. Disinfection. Water naturally carries biological life forms that can cause diseases. These waterborne pathogen organisms can cause the types of diseases that may cause harm to humans. So of course, there's biological life in water that we cannot see, and that's in the form of viruses, bacteria, and we need to inactivate those constituents in the water so that it doesn't affect in any type of gastrointestinal disease of our customers in our service area. One of the cleansing processes in the treatment of safe water is called disinfection. Disinfection is a process designed to kill and activate most microorganisms in water or wastewater, including essentially all pathogenic disease-causing bacteria. There are several ways to disinfect, with chlorination being the most frequently used in water and wastewater plants. There are a couple factors that influence disinfection: pH, temperature, turbidity, reducing agents, microorganisms. pH, the pH of water being treated can alter the efficiency of disinfectants. Chlorine, for example, disinfects water much faster at a pH around 7 than at a pH over 8. The lower the pH goes, the better chlorine will disinfect, and the less contact time you will be required to reach full disinfection. Temperature conditions also influence the effectiveness of the disinfectant. The higher the temperature of water, the more efficient it can be treated. Longer contact times are required to disinfect water at lower temperatures. To speed up the process, operators often simply use larger amounts of chemicals. Be aware that the higher the chlorine concentration, the greater the dissipation rate of chlorine into the atmosphere. So a lot of times in the summertime when you have higher flow, some utilities may increase their chlorine targets to reach better disinfection if your chlorine contact basin, chlorine contact chamber is incorrectly sized. And in the winter months, luckily in the winter, you have typically their demand goes down and you have more contact time with the water. And because of the water temperature, you'll need that time. Turbidity. Under normal operating conditions, the turbidity level of water being treated is very low by the time the water reaches the disinfection process. Disinfections last. It's after you've removed as much as you can as far as turbidity in the water. Excessive turbidity will greatly reduce the efficiency of the disinfecting chemical or process. Studies in water treatment plants have shown that when water is filtered to a turbidity of 1 unit or less, most of the bacteria have been removed. So the name of the game from the beginning of the treatment process to the end is to remove as much as turbidity as you can. Similar with organic and inorganic matter. Organics found in water can consume great amounts of disinfectants, kind of connecting back to when I was talking about enhanced coagulation. We want to reduce the organic load, the organic carbon in the water as much as we can through our coagulation. Aluminum sulfate is really good at that, and through the front end of the process. Because if you have organic load getting through the organic carbon, high levels getting through filtration, number one, it's going to have an intense load chlorine demand on your chlorine addition. And in addition to that, you're going to form the disinfection byproducts, which are carcinogenic to consumers. Microorganisms. The concentration of microorganisms is important because the higher number of microorganisms, the greater the demand for a disinfecting chemical. The resistance of microorganisms to specific disinfectants carries greatly. Cysts and viruses can be resistant to certain types of disinfectants. So the removal process. So in each stage of the water treatment process, you are removing pathogenic organisms can be removed from water, killed or inactivated by various physical and chemical water treatment processes. So first you have your coagulation. So coagulation is going to remove 90 to 95% of pathogenic organisms, depending on which chemicals you use. Alum usage can increase virus removal up to 99%. Sedimentation, so 20 to 70% of pathogenic organisms are removed by sedimentation. Filtration, filter water through granular filters is an effective means of removing pathogenic and other organisms from water. The removal rates vary from 20 to 99 or plus percentage, depending on the coarseness of the filter media and the type and effectiveness of pretreatment. So that is the reason why from the beginning of the treatment plant to the end of filtration, you want to remove as much as you can, because it's less work for your disinfectant to do. Disinfectant chemicals such as chlorine are added to water to kill or inactivate whatever's left. There are other types of disinfectants. There's UV. Can be used to destroy pathogenic microorganisms. To be effective, the rays must come into contact with each microorganism. The UV energy disrupts various organic components of the cell, causing a biological change that is fatal to the microorganism. These systems have not had widespread acceptance because of the lack of measurable residual and the cost of operation. Currently, use of ultraviolet UV rays is limited to smaller local systems, industrial applications. Advances in UV technology and concern about the DBPs produced by chlorine have prompted renewed interest. So UV has become a little bit more popular recently. Number one, there is no disinfection byproduct, and costs have been going down, and it has been, and as we begin to find more sources of water, maybe there's a wastewater treatment plant nearby, UV disinfectant has become more ideal for some utilities. So another way to disinfect is heat. Heat has been used for centuries to disinfect water. Boiling water for about 5 minutes will destroy essentially all microorganisms. Heat cannot be used on industrial scale. It's too expensive. Ultrasonic waves have been used to disinfect water on a limited scale. Sonic waves destroy microorganisms. Again, you can't use that on an industrial scale. Iodine, bromine bases can inactivate certain pathogens. And then there's ozone. Ozone has been used in the water industry since the early 1900s, particularly in France. Although ozone is effective in disinfecting water, its use is limited by its solubility. The temperature and pressure of water being treated regulate the amount of ozone that can be dissolved in the water. Many scientists claim that ozone destroys all microorganisms. Unfortunately, significant residual ozone does not guarantee that water is safe to drink. So there's pros and cons to ozone as well. It's expensive. It has to be generated on site. Mainly smaller utilities can afford it, so the larger utilities will. And then there's chlorine. Chlorine is a greenish yellowish gas with a penetrating and distinctive odor. The gas is 2.5 times heavier than air. Chlorine has a high coefficient of expansion. Chlorine by itself is non-flammable and non-explosive, but it will support combustion. Chlorine residual is important. Chlorine is not only an excellent disinfectant, but also reacts with iron sulfide and many taste and odor producing compounds to help improve the quality of treated water. There are 2 types of chlorine residual. There's free chlorine residual, and then there's combined. The good thing about the chlorine residual is we want an active disinfectant to remain in the water as it's sent to the distribution system, because we want it to be continually disinfect. Because there are things that happen in the distribution, main breaks, tanks may have infiltration of rodents, and as long as you have a good strong chlorine residual, the water is safe to drink. Free chlorine residual refers to chlorine gas. Chlorine hypochlorous acid is HOCl, and the hypochlorite ion is OCl. Combined residual chlorine refers to the chlorine ammonia compounds, monochloramine, dichloramine, and trichloramine. These are both types of disinfectants. Free chlorine is going to give you, it's much more volatile. You're going to get a lot more DBP formation, but it's also the strongest disinfectant. The combined residual, when you're forming chloramines, it's a weaker disinfectant, but it's more stable, and you're not going to form any disinfection byproducts. Depending on your system, you may prefer one or the other. And that would depend on the DBPs in specific parts of your system. Moving over to corrosion control. Factors influencing corrosion. There's physical factors, there's system construction, system pressure. High pressure systems corrode more greatly. Pressure management becomes important. Lower pressured systems tend to corrode less. The soil moisture, stray electric current, and temperature. Effects of chemical factors. Various chemical factors greatly influence corrosion. pH, alkalinity, chlorine residual, levels of dissolved solids, dissolved gases. Methods of controlling corrosion. In water treatment, calcium carbonate saturation is probably the most popular. Reducing corrosive water is almost always accomplished by treating the water with chemicals so that the water is saturated or slightly supersaturated with calcium carbonate. These chemicals should be fed after filtration. Determination of chemical. So it depends on the water quality goals and ultimately price. There's quicklime added to waters that have low hardness, low alkalinity in order to form calcium carbonate barrier in distribution mains. And there's caustic soda added to waters with high levels of hardness and alkalinity because there is already sufficient calcium alkalinity to form calcium carbonate. But the pH must be increased to reach saturation conditions. So lime, there have been improvements with lime. There's liquid lime now. So previously it was difficult to handle because it was a powder form. Everyone knows any type of powder chemical in water treatment is very tough to manage. It has to be cleaned periodically, and the feed may not be accurate if the hopper gets clumped up. A lot of moisture can impact it as well. Messy, cakes, inhalation hazards, so lots of safety hazards. Caustic is more accurate to feed. It's a liquid. It's very dangerous, and it's actually one of the more expensive chemicals. Chemical dose is dependent on the pH desired. So pH desired is based on the Langeler saturation index, where you can find which point in which you will have the calcium carbonate saturated and precipitate out of the water onto your pipe. And there's also cathodic protection systems, and this is more for the exterior of the pipe in your distribution system. So we're going to add, we're doing calcium carbonate precipitation in the drinking water to coat the inside of our pipes. But on the outside of the pipes, you're going to use a cathodic protection system if it's not coated with a polymer or concrete. So used to reduce or inhibit corrosion of metal exposed to water or soil. Key to the system is the use of an auxiliary anode of expendable metal, typically zinc, that is immersed or buried in the soil or water. All cathodic protection systems pass current through the soil or water from anodes connected to the structure that is to be protected. Protection of flocculators. So at the treatment plant, you will also use automatic cathodic protection control devices, which provide precise corrosion control nearly in all conditions. So moving over, in connection with corrosion, lead, copper rule. Lead is a common, natural, and often useful metal found throughout the environment in lead-based paint, air, soil, household dust, food, certain types of pottery, etc. Lead in drinking water, although rarely the sole cause of lead poisoning, can significantly increase a person's total lead exposure. When water stands in lead pipes or plumbing systems containing lead for several hours or more, the lead may dissolve into the drinking water. Lead copper rule was established in 1991. Maximum contaminant level goals, action levels are established for lead and copper. Lead and copper monitoring, treatment technique for lead and copper, including optimal corrosion control techniques and public notification and education, which is very important. There's monitoring requirements. Lead copper monitoring must be taken from high-risk areas, homes with lead solder installed after 1982, homes with lead pipes, homes with lead service lines. Maximum contaminant goals, 10% of samples taken in the system cannot exceed the action level. Actually, the goal of the lead copper rule is essentially to get rid of all lead service lines in a system. And if you do have them, you need to get rid of them. And if you're detecting lead, you need to do something about it. Lead action level is 0.015 milligrams per liter. Copper action level is 1.3 milligrams per liter. Treatment requirement, pH alkalinity adjustment to precipitate out the calcium carbonate to coat the pipes so that there is a barrier between the water and whatever is in the pipe. Calcium adjustments to form protective calcium carbonate films inside the plumbing. Phosphate or silica-based inhibitor addition. Lead service line replacement. All public water systems that continue to exceed the lead action level after installation, optimal corrosion control treatment. Replacement of 7% of their lead service lines per year. Total replacement of the entire lead service line unless it can demonstrate that it does not control the entire line. A maximum of 15 years to complete the lead service line replacement. Public education is huge. Mailing out of notices, announcements in major local daily, weekly newspapers, distribution of pamphlets to schools, healthcare, daycare facilities, submittal of public service announcements to at least 5 of the largest radio and television stations in the area, flushing taps before use, cooking with cold water rather than hot tap water, checking new plumbing for lead, solder, testing their water for lead. California, Title 22, and moving over to the regulation side is a good source of, this is where you should go in seeing the most up-to-date information about California water laws. Safe Drinking Water Act in 1974 really drove a lot of the regulation. It was signed into law, giving the federal government authority, through the EPA to set national drinking water standards, regulating the levels of contaminants in the drinking water, require public water systems to monitor, report their levels of identified contaminants, establish uniform guidelines specifying the acceptable treatment technologies for cleansing drinking water of unsafe levels of pollutants. In those regulations, there's primary standards and secondary standards. The primary standards establish maximum MCLs based on health significance of the contaminants. Secondary standards are more aesthetic. Public water system is defined as the system with 15 service connections, regularly serves an average of 25 individuals daily, at least 60 days out of the year. Surface water treatment rule was established. It established turbidity requirements, combined effluent turbidity, combined filter effluent, limit of 0.3, 95% of the time, never to exceed 1 MTU, and disinfection requirements, 99.9% removal of Giardia, 99.99% removal of virus, also known as 3-log, 4-log removal. Conventional systems using their conventional or direct filtration must achieve a filter water turbidity of less than or equal to 0.3, 95% for conventional treatment plants. It's different if you have a different treatment train. This limit may be increased by the state to 1 MTU if the system proves it can effectively remove Giardia at such turbidity levels and never exceed 1. Total coliform rule. Coliform must be absent 95% of samples collected from your TCR taps. If a routine sample is positive, the water supplier shall collect a repeat sample within 24 hours of being notified of the positive result. 3 samples are to be collected: one the original sample, 1 upstream, 1 downstream within 5 service connections. So at the treatment plants, we are requiring low turbidity levels and also to maintain disinfection. And then when you get out to the system, we're monitoring for elevated coliform levels to see if there's any type of significant rise in bacterial counts. A system collecting at least 40 samples per month has a total coliform positive routine sample followed by 2 total coliform positive resamples. A system has a sample which, let's see here. So a significant rise in bacterial counts is a system collecting at least 40 samples per month and has a total coliform positive routine sample followed by 2 total coliform positive repeat samples. So they would call that a significant rise in bacterial counts. And a system that has a positive for fecal coliform or E. coli, a system that fails the total coliform MCL. So that would be regarded as a significant rise. Total coliform MCL results of all samples collected in a calendar month shall be included in determining compliance with the total coliform MCL. A violation of TCR MCL occurs when a public water system, which collects 40 samples per month, more than 5% of samples are TC positive, or for a public water system that collects fewer than 40, that's more than 1 sample is TC positive, or any repeat fecal or E. coli positive, or any repeat fecal coliform positive or E. coli positive routine samples, total coliform positive. So again, your TCR taps are to monitor what's going on in the system and to monitor for significant rise in total coliform, which may indicate there's something going on and would prompt you to investigate. Public notifications, tier 1 notification as soon as possible. 24 hours, this is an acute, immediate risk to human health or unknown risk. Tier 2 notification is within 30 days after learning of a violation, and a tier 3 notification within 1 year. Typically in the annual consumer confidence report. Disinfectants and disinfection byproducts rule. So these are the MCLs of the disinfection byproduct rule. THMs, it's going to be 0.08 milligrams per liter as MCL. And haloacetic acid is going to be 0.060. And bromate is 0.010. Bromate is typically for systems using ozone as a disinfectant. They're going to measure for bromate. And all this is done on a locational running annual average, not the bromate, but the THMs and the HA5s. So your system, the regulators, our regulator will determine, well, actually we'll do a distribution system. We'll take a look at the distribution system. We'll find locations which the water age is typically the most, the longest the water will be there in the system. And then at those points will be where we'll measure for THMs and HA5s for quarterly samples to see if the level is gone above the MCL. And it's based on average, a 4-month average, a 4-quarter average, I'm sorry. There you go. Results are based on location running annual average. Also set maximum residual disinfectant level. Chlorine, it's 4 parts per milligrams per liter. Same for chloramines, tighter on chlorine dioxide. Monitoring requirement. The LRAA is based on an average of the quarterly samples collected per location in the distribution system reported every quarter in the state. There are requirements for enhanced coagulation. Require removal of TOC by enhanced coagulation, again, in an effort to reduce DBP formation based on alkalinity and TOC in the source water. Emerging contaminants, lead copper rule revisions, PFAS, microplastics. I think that's it. I know that was quick and we didn't have much time. But that was the quick and dirty. Any questions?
Thanks, Daniel. We appreciate any questions that you might have or comments, anything that you'd like to discuss with our speaker, Daniel. You can type in the chat, or if you feel more comfortable just talking out, you can do that as well. Yeah.
Well, hope everyone's doing well today.
All right. Daniel, do you have any knowledge or comments about where we are with the state certifications, and maybe you have some insight?
So I know that the state has delayed a lot of they delayed the fall test and this year the spring test as well. But I do know that they're doing these smaller group tests, and they're working on an online format. So I know for the water treatment operators for East Bay Mud, we had to apply for, emergency type test. And these are new operators that, is a part of their job description to have a license. And so we applied and we were granted authorization to send them to take a test. And I think those tests were done in Sacramento. We'll see what happens with the pandemic. I think 2021 is looking better and better as, vaccine may be coming soon, and hopefully we can get through the winter. I'll say that water treatment continues on. We've never missed a beat, and we are essential to our communities. So we always are going to be here 24/7.
We have a question here, Dan. Says, what can we expect as far as math goes? Coming from Vanden Hughes.
So math, math would be a separate class. There is a sheet on the California DDW website. If you've gone through the Ken Curry latest volume, there's a lot of good math examples in that book. You're probably going to get some chemical dosage questions. You're going to get detention time questions, possibly CT, but a lot of those examples are in that book. And we didn't do a math prep this time, but maybe we should consider that for next time.
Yeah, you can't cover it all.
Yeah, it's tough to cover. I mean, in 45 minutes, it is a lot to cover. I would say for the T3, T4, usually, well, at least for the T4, usually people have been operating for a little bit, and they've got a good idea of what's going to be on that test. Reading the material through, a Ken Carey book is always beneficial, and going through some of those math problems, and also, downloading the math cheat sheet where it gives you the formulas and being familiar with all of them, filter load rate, chemical dosage questions. Those are always beneficial when you're taking that test. Usually what I do too is I do the math first. When the tests were in person, I would do the math first and then kind of do the questions last. It's just something that I always felt, once I got the math out of the way, I could take on the regular questions.
Okay. Well, we have some folks commenting about the plans for the computer-based testing, as you were talking about, Dan, that they're working on with the state.
Yeah, last I heard they were, but I haven't received an update on that. But I guess the plan is to do it every month, actually, and computer-based test. And I'm not certain if they would do that, administer it from your desktop at home, or if you'd have to go to a location to do it. Those details I don't have. I know Annette, wasn't she, she had, I forgot who we had speak.
Yes, she was there. She's she works closely with us.
Yeah, so she usually gave us a really good update on where we were with the tests and how they were gonna improve it. And
right.
So I don't know if she's speaking today.
No, not today.
Okay, so
Leo Bardo is asking, he said he's going to be taking the T2 and he's looking for advice and what can he expect from it.
So we're going to get, well, if it was an in-person test, you know, usually you'll be in an auditorium, make sure to bring a calculator. It can't be scientific. Sometimes they'll recommend you not have a solar calculator because you never know how much light will be in there. Have some number 2 pencils ready, you know, and you're going to be seated in between people taking different tests. They don't want people sitting next to each other if they're taking the same test. And I believe you're given plenty of time, maybe 3 hours to complete all the tests. And yeah, when you start, yeah, just bubble in the best answer. I believe it's all multiple choice. Even the math is now multiple choice. When I took the test, the math wasn't. It was just you had to figure out the answers, but now it's all multiple choice. So.
Yeah. All right. Well, we're getting a lot of comments, Dan. Thanking you for informative information and
no problem.
Presentation and all of that. And we want to thank everyone for being with us today and thank Dan for giving us this great presentation.